Hi everyone, welcome to part 2. Now in this part we'll look into different kinds of probability that we have. Now each kind of probability will be defined first with its literature and then with its mathematical representation. By literature we basically try to understand with words what that kind of probability deals with, and then in mathematical terms we'll define it, what should be, how should we calculate, and what should be the probability. So in this part we'll deal with different kinds of probability and define them accordingly. So let's move into the lecture and watch the video for part 2. Hi, continuing with probability, let's look into this part as different ways in which a probability is defined. Now we know the basic definition. Continuing on with it, we see probability is termed under different categories. First of all, experimental probability. Now the experimental probability is based on the observations obtained from probability experiments, like different events are done, and in each experiment based on that, when we conclude, this is how we represent it: the number of event occurrences by total number of observation. So this is one of the ways which probability is defined. The experiment probability of an event E is the relative frequency of the event. Now the relative frequency means different experiments are done and the cumulative is taken. So the relative frequency at which the experiment is conducted and the observations is hence explained by number of event occurrences by total number of observations. Next is subjective probability. Now subjective probability is a little interesting. Why? Because it's mostly based on intuition and guesstimation. So basically subject probability is the probability measure resulting from intuition, educated guesses and estimation. Now thus there is no formula to calculate that. Okay, there is no particular formulation for that. So it is usually found by consulting an expert. Law of large numbers. Now an experiment is repeated over and over. The experimental probability of the event approaches the theoretical probability of the event. Basically, theoretically we have an idea how the event will perform, right? Now if we conduct a large number of experiments, repeat those over a large span of time, that will give me the number which is closer to the theoretical probability of an event. The greater the number of trials, the more likely that the experimental probability of the event will be equal to the theoretical probability. Now the idea of probability is very interesting. Probability, it is the science of behavior. Okay, like we know that it is a mathematics of chance, and that is how we define it as the science of a behavior. Now the chance behavior is unpredictable, obviously, in the short run, but has a regular and predictable pattern in the long run. Now if we toss a coin, right, it can either come head or a tail. So we cannot be sure of how many times the head will come, how many times the tail will come. But if we do the same toss at over 100 period of time, let's say I get 55 heads and 45 tails. So we understand that the likeliness of getting a head may be more as compared to getting a tail. Now, this is why we use probability to gain useful results from random samples and randomized comparative experiment. Similarly, if you look into these things, when we roll the die, we don't know for sure what it will happen. But when we roll the die for n number of times over a period of 100 events, then we will understand what is the frequency of a particular number coming. Okay, same is with the cards. Now, the randomness and probability are mutually exclusive. Now, when we define random, individual outcomes are uncertain, but there is a regular distribution of outcomes in a large number of repetitions. Same, continuing with the same theory that we have defined, we continue again how randomness is defined. Now the relative frequency proportional to the occurrence of an outcome settles down to one value over the long run. Now that one value is then defined to be a probability of that outcome. So basically when we conduct an experiment over a long period of time, over a set of 100,000 maybe, then we get to understand what is the actual probability that we have to consider. Now probability models. The sample space, as we have defined, of a random phenomena is the set of all possible outcomes. An event is an outcome or a set of outcomes. Now the probability model is a mathematical description of long run regularity consisting of sample space S and way of assigning probability of the events. Okay. Now the rules of probability. It is important to know all the rules of the probability to solve any question accurately. Now when we define probability rules, the first and the most important rule is any probability is a number between 0 and 1, as we have already discussed why. A probability can be interpreted as a proportion of times that a certain event can be expected to occur. Now, if the probability of the event is more than 1, then it will occur more than 100% of the time, which is impossible. Let's look at this part. Okay, this is a very good animation that will help you understand how a probability works. So when we have such a case, look at this. There it is a set of 8 balls, okay, in which 3 are red and 5 are green. So the ratio of red marbles to green marbles is 3:5. The probability of selecting a red marble is 3 out of 8. Similarly, now the rule 2 says all possible outcomes together must have as a probability 1. You see this? This is nothing but it basically defines different probabilities. Okay? This might be a certain probability, this might be a certain probability, and this. Now when we add all of them, all these, okay, it is like a pie. Occurrence of a particular event might be this much, right? And similarly like this. But if you add them all, okay, for a particular event, if I add all the experiments, it will give me the net as 1. Because some outcomes must occur on every trial, the sum of the probabilities for all possible outcomes must be exactly 1. If the sum of all the probabilities is less than or greater than 1, then the resulting probability model will be incoherent. Basically, it will not exist. Now, third rule is also very interesting. If two events have no outcomes in common, they are said to be disjoint. How do we understand disjoint? The probability that one or the other of two disjoint events occurs in the sum of their individual probabilities. Basically, age of the, let's understand with this example, age of the woman at first childbirth, 20, 25%, 20 to 24, 33%. Then what would be 25 plus? It would be based on the total calculation. Basically, the sum of all these three must be 100. So we know these two, we subtract it from 100, we will get the number as 42 as given over here. So this is what we understand in rule 3. Our rule 4 says that the probability that an event does not occur is -1, the probability that the event does not occur. If any probability is in negative, chances are that that event does not occur. Okay? But as we know that the probability of any event can never be negative. Okay? If you see that it is remotely coming negative, then understand that the event will not occur. Now, as a jury member, this is an example for that. You assess the probability that the defendant is guilty to be 0.8%. Okay, that is 8 out of 10. Thus, you must also believe that the probability that the defendant is not guilty is 0.2. in order to be coherent, consistent with yourself. Alright. Now the probability that a fight will be on time is 70. Then the probability that it will be late is 30. Okay. So these are the cases. Basically it is mutually exclusive with respect to it's happening and it's not happening. Now the mathematical notations for probability I have already defined. From rule 1 it says that the probability will be 0 to 1. Number 2 says that the probability sample space is always 1. Two events are disjoint, that is PA or B, PA plus PB, basically the net. And rule 4 says that if for a particular event not to occur, 1 minus PA. Okay. Now in this next case we will see random phenomena. Random phenomena are like roll pair of fair die and count the number of pips on the up faces. Now find the probability of rolling a 5. Okay, like when we roll this die, okay, I throw it, what is the probability that it will be a 5? Now rolling a 5, that is net sum, is defined by these numbers. So getting these is defined by this. So the net probability will be like this. Now discrete probability, finite countable number of outcomes. Basically we assign a probability to each individual outcomes where the probabilities are numbers between 0 to 1 and the sum to 1. The probability of any event is the sum of the probabilities of the outcomes making up the event. Now if we see the previous slide for that example, we understand how we mean this. Okay. Continuous probabilities. Now the intervals of outcomes basically defines the continuity of a probability. Okay. It cannot assign a probability to each individual outcome because there are an infinite number of outcomes. Probabilities are assigned to intervals of outcomes by using areas under density curves. As a density curve has area exactly 1 underneath it. Now the corresponding to the total probability to be 1. Now assigning probability for random number examples, random number generates give outputs spread uniformly across the interval 0 to 1. Okay, basically randomness can be defined in no other way other than that it spreads over the scale of 0 to 1. Now to find the probability of getting a random number is less than or equal to 0.5 or greater than 0.8. You see, this is how we define that area. This is the area where my 0.5 will come and this is the area for 0.2 to come. So this is the probability of a particular randomness that can be broadly classified. Now to define it mathematically, we see that Px, it has to be less than or equal to 0.5 or it has to be greater than 0.8. So to get that, I have my sample space is or the occurrence is reduced to 0.5 plus 0.2. So the probability, net probability would be 0.7 or 7 by 10. Now the normal probability models that you will be dealing mostly with often are the dense curves used to assign probability to interval outcomes in the normal curve. Now the normal distribution are probability models. Okay, probability can be assigned to interval of outcome using standard normal probabilities in table A. Okay. Now the techniques for finding such probability is found in your given chapters. Now let's look at example. Okay. Let's say I need to convert observed values of the endpoint of the interval of the interest to standardized score. Then the probabilities from table A. You see, this is the table that we were talking about that was asked in our previous slide. So if you look at this, how do I convert this to a particular value? To do this, we take out the whole sample space and we find what would be this percentage. So this percentage divided by the net area will give you the probability of this particular event. Now the random variables. Now random variable is a variable whose value is a numerical outcome of a random phenomenon. Okay, it is simply defined as any of the alphabet. The probability distribution is an important term. Probability distribution of a random variable is what defines its randomness. Basically, if there are random events that occur together, if we take probability distribution, it will give you a pinpoint location or at least clearer picture that the event can be predicted or it has a settled area. Okay, like we defined for 0.5 plus 0.2, that see a particular event is occurring for a less than 0.5 or greater than 8. Okay, but how to get that data? That is defined by probability distribution. Getting n number of data for a random experiment or random variable will define its unrandomness, and it will give you the exact values that you require to define its probability. Now, if we take that, if that has to have a finite list of possible outcomes, okay, and with probabilities assigned to each of these outcomes are called discrete. So discrete probabilities are calculated for each random variable, and its probability distribution is taken to calculate the probability of a random variable. The random variables that can take on any value in an interval with the probability it gives as area under the density curves are called the continuous probability. So if you look at these things, these will be the random examples of the random variables that we have, and this continuous curve is defined by the curve given in our table A. Now the discrete random variables, number of pets owned, number of days of the month, how many days of the class missed, so these are the discrete random variables. Continuous random variables is weight, temperature, time taken to travel to work. These are the continuous random variables. Now the personal probability. Personal probability is the degree to which a given individual believes the event in question will happen. Okay. Personal belief or judgment defines personal probability. Now used to assign probability when it is not feasible to observe outcomes from a long series of trials. Assigning the probabilities must follow the established rules of probabilities between 0 to 1. Example, probability that an experiment never performed surgery will be successful. Probability that the defendant is guilty, again personal probability. Probability that you will receive a B in this course, again personal probability. Probability that your favorite baseball team will win the World Series in 2020. So events like this define that. Let's look into the examples that we have studied, examples based on the topics that we have just studied. A card is drawn from a well shuffled deck of 52 cards. Okay, we need to calculate that the card will be an ace or not be an ace. Okay, so we know that in a deck of cards there are 4 aces, right? Now to get an ace, it has to be 4 out of that 52, right? So the probability of getting an ace is 4 by 52, and not getting an ace can be 48 by 52, right? So it is defined as EA naught. So these are the probability for these 2 cases. You see? Now the next example is, there are 40 students in the class 10th, okay, of a school, of whom 25 are girls and 15 are boys. The class teacher has to select one student as a class representative. She writes the name of each student on a separate card okay, being identical, and then she puts the card in the bag and stirs them thoroughly. Then she draws one card from the bag. What is the probability that the name written on the card is of a boy or a girl? If you look into this, there are 40 students and only one name has to be chosen. The number of possibilities is 40, so that is the sample space. The number of outcomes for a card with the name of a girl is 25. Okay, you need to understand this why. Why? Because there are 25 girls out of 40, so the chances of a number coming, the name coming out to be girl is 25. Therefore, probability of the card with the name of the girl is P 15 by 40, that is 3 by 8. So we can determine P boy by 1 minus P. So that is defined by this. Alright. Actually this is 25. Okay. So this will give me 5 by 8. Alright. You see this is 25 here. So this will give me 5 by 8. And this probability of getting a boy is 3 by 8. So guys, that was all for our probability chapter. At the end of part 2, we have come to the end of our probability chapter. In this part, we have learned about different kinds of probability and how it is mathematically represented. Now by the end of it all, we now know how to solve the questions of probability. We know how to define sample space, we know how to calculate different events and how to take out probability distribution. We also know the frequency with which we can calculate a probability for a random event. Now, that was all in our probability lecture, guys. So in this next part that we have, we'll solve previous year CBSE questions that have come, and we'll look into the different kinds of questions that we deal in our board exams. So stay tuned for part 3.